In this session, we will learn how to prove irrationality of certain numbers. A number is irrational if it cannot be represented in the following form: P by Q, where P and Q are integers and Q is not equal to 0. For example, root 2, root 3, root 7, root 2 divided by root 5. Such numbers are irrational, and we will prove that they are irrational using the fundamental theorem of arithmetic. Now we will prove three things in this session. Firstly, we will prove the irrationality of an irrational number. Secondly, we will prove that the sum or difference of irrational numbers is also irrational. And thirdly, we will prove that the product of a non-zero rational number and an irrational number is also irrational. Let's take some problems. Let's prove that root 2 is an irrational number. Let us assume on the contrary that root 2 is a rational number to begin with. Then there exist positive integers a and b such that root 2 is equal to a divided by b, where a and b are co-prime and their HCF is 1. So we begin with root 2 is equal to a divided by b. Squaring both sides, we get root 2 the whole square is equal to a divided by b the whole square. So that means 2 is equal to a square divided by b square. Cross multiplying, we get 2b square is equal to a square. So that means 2 completely divides a square. If 2 completely divides a square, 2 also completely divides a, using the fundamental theorem of arithmetic that we learnt earlier. Let's call this inference 1. Now if 2 completely divides a, that means a is equal to 2c for some value c. Squaring both sides, we get a square is equal to 4c square. A square is also equal to 2b square. So we can equate 2b square as 4c square. Dividing both sides by 2, we get b square is equal to 2c square. This means 2 completely divides b square as well. Or else we can say 2 completely divides b using the same fundamental theorem of arithmetic. Let's call this inference 2. From the inferences 1 and 2 we saw earlier, that is 2 completely divides a and 2 completely divides b as well, we get that 2 is a common factor for both a and b. But this contradicts our earlier assumption that a and b have no common factors other than 1. This means our assumption is wrong. Our assumption was that root 2 is a rational number. Hence, root 2 is an irrational number. Next, we will generalize our earlier problem and prove that any prime number p, for any prime number p, root p is irrational. Again, let us assume on the contrary that root p is rational. Then there exist positive co-primes a and b such that root p is equal to a divided by b. Squaring both sides, we get p is equal to a square divided by b square. Cross multiplying, we get b square into p is equal to a square. So this means that p completely divides a square. And using the fundamental theorem of arithmetic, we can prove that p completely divides a as well. This again means that a is equal to pc for some integer c. Now b square p is equal to a square. So b square p is equal to p square into c square. This means that p completely divides b square. And we can prove that p completely divides b also using the fundamental theorem of arithmetic. Since p completely divides a and p completely divides b also, this contradicts our earlier assumption that a and b are co-prime. If a and b were co-prime, then they should not have the same factor. Therefore, we prove that root p is irrational. Let's solve another problem. Given that 3 and 5 are two prime integers, let's prove that root 3 plus root 5 is an irrational number. As usual, we start by assuming that root 3 plus root 5 is a rational number, which means that it can be represented in the form a by b, where a and b are co-prime and b is not equal to 0. So root 5 is equal to a by b minus root 3. Squaring both sides, we get root 5 the whole square is equal to a by b minus root 3 the whole square. Expanding the terms, we get 5 is equal to a square by b square minus 2 root 3 ab plus 3. Bringing the numerical terms on one side, we get 5 minus 3 is equal to a square by b square minus 2 root 3 a by b. So 2 is equal to a square by b square minus 2 root 3 a by b. So 2 root 3 a by b is equal to a square by b square minus 2. Multiply and divide the term minus 2 by b square so that the denominator is same, and we can add a square and minus 2b square to get 2 root 3 a by b is equal to a square minus 2b square the whole divided by b square. Taking 2a by b to the other side by cross multiplying, we'll get root 3 is equal to a square minus 2b square divided by 2ab. Here we can see that root 3 is being represented as something divided by something. But root 3 is rational. So this is a contradiction. So our initial assumption that root 3 plus root 5 is rational is also not correct. This means that root 3 plus root 5 is irrational. Let's go to the next problem. Let's prove that 3 root 2 is irrational, or for that matter, any rational number into an irrational number is irrational. Let's start by assuming that 3 root 2 is rational, which means that we can find co-prime a and b where b is not equal to 0 such that 3 root 2 is equal to a divided by b. That means root 2 is equal to a divided by 3b by taking 3 on the denominator of the other side. Since 3a and b are integers, a divided by 3b is a rational number, which means that root 2, which is equal to a divided by 3b, is also a rational number. But we know that it is a fact that root 2 is an irrational number. It's the square root of a prime number, so it's irrational. This means that our initial assumption that 3 root 2 is rational is incorrect. Hence, we conclude that 3 root 2 is irrational. We now come to the next part of our session, revisiting rational numbers and their decimal expansions. Let's have a small recap of what we've learned in the previous classes. We've learned in the previous classes that the decimal expansion of a rational number can be either terminating or non-terminating repeating. Examples of terminating decimal expansions of rational number are 5 by 4 and 7 by 25. If we find the value of 5 by 4 using the long division method, after 2 decimal places in the quotient, the remainder becomes 0 and the division is done. Since the remainder becomes 0 in the long division method, these numbers are terminating decimal numbers. But if we find the value of 1 by 3 using the long division method, we can keep on adding decimals to the quotient, but the remainder will never become 0. This is why these decimal expansions are non-terminating and repeating. To represent these numbers, we add a small bar on top of the repeating decimals. 1.33333 is represented as 1.3 with a bar over 3. 4.54545454 is represented as 4.54 with a bar on the 54. In this session, we will learn the conditions which determine whether a rational number will be terminating or non-terminating repeating. You know that a rational number having a terminating decimal expansion can be written as a rational number whose denominator is some power of 10. For example, 0.457 is equal to 457 divided by 1000, which is equal to 457 divided by 10 cubed. 0.050456 is equal to 50,456 divided by 1 followed by 6 zeros, which is equal to 50,456 divided by 10 to the power of 6. Similarly, 4.7345 can be represented as 47,345 divided by 10,000, which is 10 power 4. So, the number can be represented as 47,354 divided by 10 to the power of 4. Theorem 1. Let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form of p by q, where p and q are co-primes, and the prime factorization of q is of the form 2 to the power of m into 5 to the power of n, where m and n are non-negative integers. Let us now see if the converse of this theorem is true or not. Let a by b be a rational number in the lowest form such that the prime factorization of b is of the form 2 to the power of m into 5 to the power of n, where m and n are non-negative integers. There will be 3 cases which are possible because of the values of m and n. Case 1 will be where m is equal to n. In this case, we have a divided by b is equal to a divided by 2 to the power of m into 5 to the power of n, which is 2 to the power of m into 5 to the power of m itself, because m is equal to n. So, multiplying 2 and 5, we get a by b is equal to a divided by 10 to the power of m. Case 2. When m is greater than n. In this case, we have m is equal to n plus p, where p is a positive integer. A by b is equal to a divided by 2 to the power of m into 5 to the power of n. Multiplying the numerator and denominator by a term 5 to the power of p, we get a by b is equal to a into 5 to the power of p divided by 2 to the power of m into 5 to the power of n plus p. We get 5 to the power of n plus p by the rules of exponents, that 5 to the power of n into 5 to the power of p is equal to 5 to the power of n plus p. Since n plus p is equal to m, we get a into 5 to the power of p divided by 2 to the power of m into 5 to the power of m, which is equal to c divided by 10 to the power of m, where c is equal to a into 5 to the power of p. Case 3. When m is lesser than n. In this case, we have n is equal to m plus p, where p is a positive integer. A by b is equal to a divided by 2 to the power of m into 5 to the power of n. Multiplying the numerator and denominator by a term 2 to the power of p, we get a by b is equal to a into 2 to the power of p divided by 2 to the power of m plus p into 5 to the power of n. Since m plus p is equal to n, we get a by b is equal to a into 2 to the power of p divided by 2 into the power of n into 5 to the power of n. Multiplying 2 and 5, we get a by b is equal to c divided by 10 to the power of n, where c is equal to a into 2 to the power of p. Thus, a rational number whose denominator is of the form 2 to the power of m into 5 to the power of n, where m and n are non-negative integers, can be converted to an equivalent rational number of the form c by d, where d is a power of 10. We saw in the earlier lesson that a rational number whose denominator is of the form 2 to the power of m into 5 to the power of n, where m and n are non-negative integers, can be converted to an equivalent rational number of the form c by d, where d is a power of 10. So d would be 10 or 10 squared or 10 cubed or 10 to the power of 4 or anything like that. Let's see a few examples below. Consider the rational number 7 by 8. 8 is 2 cubed. So 7 by 8 can be written as 7 divided by 2 cubed. Multiplying the numerator and denominator by 5 cubed, we get 7 into 5 cubed divided by 2 cubed into 5 cubed. So 7 into 125 divided by 2 into 5 the whole cubed. 2 into 5 gives 10 and 7 into 125 gives 875. So we get 875 divided by 10 cubed. As you can see, we've converted the fraction 7 by 8 to the form c by d, where d is a power of 10, 10 cubed in the case. Consider 189 divided by 125. 125 is 5 cubed. So we can write 189 by 125 as 189 divided by 5 cubed. Multiplying the numerator and denominator by 2 cubed, we get 2 cubed into 189 divided by 2 cubed into 5 cubed, which is 8 into 189 divided by 2 into 5 the whole cubed. 8 into 189 gives 1512. So we get 1512 divided by 10 cubed. Consider 49 divided by 500. 500 can be written as 4 into 125. 4 is 2 squared and 125 is 5 cubed. So we get 49 divided by 2 square into 5 cubed. Multiplying and dividing by 2, we get 49 into 2 divided by 2 into 2 squared into 5 cubed, which is 98 divided by 2 into 5 the whole cubed, which is 98 divided by 10 cubed. Consider 2139 divided by 1250. 1250 is equal to 2 into 625. 625 is equal to 5 to the power of 4. So we can write the fraction as 2139 divided by 2 into 5 to the power of 4. Multiplying and dividing by 2 cubed, we get 2139 into 2 cubed divided by 2 to the power of 4 into 5 to the power of 4, which is 2139 into 8 divided by 2 into 5 the whole to the power of 4, which is 17,112 divided by 10 to the power of 4. So as you can see, in all these cases, we've divided a rational number whose denominator is of the form 2 to the power of 5 into 5 to the power of n to a form c by d, where d is a power of 10. As we saw, 7 by 8 was got to be equal to 875 divided by 10 cubed, which is equal to 0.875. 189 by 125 was 1512 divided by 10 cubed, which is equal to 1.512. 49 by 500 was 98 by 10 cubed, which is equal to 0.098. And finally, 2139 divided by 1250 was got to be equal to 17,112 divided by 10 to the power of 4, which is equal to 1.7112. This shows that the decimal expansion of a rational number whose denominator is of the form 2 to the power of m into 5 to the power of n, where m and n are non-negative integers, is terminating. Now we will learn a theorem. Let x is equal to p by q, where q is not equal to 0, be a rational number such that the prime factorization of q is not of the form 2 to the power of m into 5 to the power of n, where m and n are non-negative integers. Then x has a decimal expansion which is non-terminating and repeating. To have a clear idea of how these theorems are applied, we will look at a few solved examples. Let's try to divide 1 by 7. The long division process has been put on the right over here. The remainders at each point after the division, the long division process, will be 3, 2, 6, 4, 5, 1, 3, 2, 6, 4, 5, 1, and 3, 2, 6, 4, 5, 1 will keep on repeating. The divisor is 7 and the remainder 3, 2, 6, 4, 5, 1, 3, again 2, 6, 4, 5, 1 would have been the remainder next. Notice that 7, which is the divisor, is clearly not of the form 2 to the power of n into 5 to the power of m. So using the above theorem that we just learned, we know that 1 by 7 will not have a terminating decimal expansion. Hence 0 will not show up as a remainder, and the remainders will start repeating after a certain stage. So to conclude what we've learnt already, we have another theorem. Let x is equal to p by q be a rational number such that the prime factorization of q is of the form 2 to the power of m into 5 to the power of n, where m and n are non-negative integers. Then x has a decimal expansion which terminates. Let us now consider rational numbers whose decimal expansions are non-terminating and repeating. For example, 5 by 3 will be equal to 1.666666, 17 by 6 will be equal to 2.833333, and 1 by 7 will be equal to 0.142857, 142857, and so on. We observe that the prime factorizations of the denominator of these rational numbers are not of the form 2 to the power of m into 5 to the power of n, where m and n are integers. Let's solve a few problems. Without actually performing the long division, state whether the following rational numbers will have a terminating decimal expansion or a non-terminating repeating decimal expansion. The numbers are 17 by 8, 64 by 455, 29 divided by 443, 15 divided by 1600, 13 divided by 3125, and 23 divided by 2 cubed into 5 squared. Solution 1. We have 17 by 8 is equal to 17 divided by 2 cubed into 5 to the power of 0. So the denominator 8 of 17 by 8 is of the form 2 to the power of m into 5 to the power of n, where m and n are non-negative integers. Hence 17 by 8 has a terminating decimal expansion. Solution 2. We have 64 divided by 455, which is equal to 64 divided by 5 into 7 into 13. the prime factorization of 455 is 5 into 7 into 13. Clearly, the denominator 455 is not of the form 2 to the power of m into 5 to the power of n. Therefore, the decimal expansion of 64 by 455 is non-terminating, repeating. Solution 3. We have 29 divided by 343. 343 is 3 to the power of 5. Clearly, 343 is not of the form 2 to the power of m into 5 to the power of n. Hence, the decimal expansion of 29 by 343 is non-terminating, repeating. Solution 4. We have 15 divided by 1600. Cancelling out the common factors, we'll get 3 divided by 320. And 320 can be written as 2 to the power of 4 into 5. This means that the prime factorization of the denominator in 15 by 1600 is of the form 2 to the power of m into 5 to the power of n. Hence, it has a terminating decimal expansion. Solution 5. We have 13 divided by 3125. 3125 can be written as 2 to the power of 0 into 5 to the power of 5. This means that the prime factorization of the denominator is of the form 2 to the power of m into 5 to the power of n, where m and n are of course non-negative integers. Hence, it has a terminating decimal expansion. Solution 6. Clearly, the prime factorization of the denominator of 23 divided by 2 cubed into 5 square is of the form 2 to the power of m into 5 to the power of n. So, it has a terminating decimal expansion. What can you say about the prime factorizations of the denominators of rational numbers whose decimal forms are given below? One is 34.12345 and the other is 34.5678 bar. Since 34.12345 has a terminating decimal expansion, this means its denominator is of the form 2 to the power of m into 5 to the power of n, where m and n are non-negative integers. And since 34.5678 bar has a non-terminating repeating decimal expansion, this means the denominator has prime factors other than 2 and 5. Let us now look at some IIT JEE AIEEE level questions and try to solve them based on what we've learned in this session. If a is a rational number and root b is an irrational number, then a plus root b is known as a quadratic surd. The square root of a plus root b will be root x plus root y, where a is equal to x plus y and b is equal to 4xy. This is a trick which you must remember to solve some problems very quickly. Let's solve a few problems. Find the value of square root of 7 plus 2 root 6 plus square root of 7 minus 2 root 6. And the options are 14, root 6, 2 root 6 and 7. Let's find the solution. Let square root of 7 plus 2 root 6 be equal to root x plus root y, and since we've assumed this, square root of 7 minus 2 root 6 will be equal to root x minus root y. Then x is equal to 7 is equal to x plus y and 24 is equal to 4xy. 24 because 2 root 6 is equal to root of 24, because the 2 will go inside and 6 will be multiplied by 4. So we get 6 is equal to xy. Therefore, we know that x is equal to 6 and y is equal to 1, because only then x plus y will be equal to 7 and x into y will be equal to 6. Therefore, root of 7 plus 2 root 6 plus root of 7 minus 2 root 6 will be equal to root 6 plus 1 plus root 6 minus 1. So the plus 1 and minus 1 gets cancelled and we get the answer as 2 root 6. So the correct option is option C. Another important type of competitive examinations question is something like this one. Find the value of square root of 6 plus square root of 6 plus square root of 6, and the loop keeps going on and on. To solve this kind of a question, assume that the entire square root is equal to some quantity x. Since the loop inside the square root goes on infinitely, the quantity which is bold and inside brackets will also be equal to x itself. So we can infer that x is equal to square root of 6 plus x itself. So now squaring both sides, we get x square is equal to 6 plus x. Taking 6 plus x on the other side, we get x square minus x minus 6 is equal to 0. So x square minus 3x plus 2x minus 6 is equal to 0. We split the middle term minus x as minus 3x plus 2x over here. So from the first two terms we take x common outside, so we get x into x minus 3, and from the last two terms we take plus 2 common outside, so we get plus 2 into x minus 3. Now taking x minus 3 outside from both the terms, we get x minus 3 into x plus 2 is equal to 0. This means either x is equal to 3 or x is equal to minus 2. Since the answer cannot be negative, we take only the positive value. Therefore, x is equal to 3.